about improper integrals. Thank you, by the way, for coming the day before the break. I know I kind of made you by giving the quiz, but I appreciate it. I noticed actually right before coming to class that my laptop battery is low. It must have not plugged it in properly this morning. So if the thing just like dies, I'll just drop the mic and we'll all leave. I don't know. It's at 28%. We'll see how it goes. I don't actually know how quickly the battery runs down while I'm doing this streaming thing. We'll find out. All right. Yeah, improper integrals. Remember, this is about doing the integral sort of all the way out to infinity. And I was talking about this at the very end last time. I'll just refresh your memory a little bit. This specific example I was discussing, this is f of x equals 2 to the negative x, or you could write it as 1 over 2 to the x. It has that kind of shape to it. And what we were talking about is doing the integral. So I specifically was discussing the integral from 1 to infinity. That means you start here and you just consider this area all the way out to the right forever. And if you remember, just at the very end last time, I gave some kind of somewhat informal, but I hope convincing reason to suggest that this area, even though it goes on forever, actually this area is not infinity. In fact, it's less than 2. You can see this by sort of what I did at the end last time was draw a bunch of rectangles here. Each of these rectangles is 1/2 the height of the previous one, which means you can actually stack them all up and they don't stretch out to infinity. They stretch out to 2, which is quite a bit less than infinity. So this one, this integral here, the area under the curve, the area is finite. This is somewhat surprising. It is possible, mathematically speaking, to have an area that stretches out to the right forever, but even so, the area is not infinity. It is, like in this example, it's actually less than 2. That's what we said last time. And there are various sort of cute ways that you can say this. You can tell your moms and dads when you go home for the spring break. This shape, like this shaded area, is something that if you had this shape in real life, it would not be possible to draw a line around the outside because that line around the outside is infinitely long. It goes all the way out to the right. So all the pencils in the world would not be able to draw that line in real life. But could you paint in the area on the inside? The answer is yes. All the paint buckets in the world, actually the area is only 2. So it's not hard. So this is a shape which you could paint the area in real life, but you could never draw around the outside of it. Very strange, in my opinion. And your parents will say, this is what I'm paying all that money for? This is somewhat a ridiculous way of describing the situation, just because when I say in real life, of course, this shape can't exist in real life because it stretches on forever. But it's an interesting and somewhat abstract thing. This is still actually useful in the real world. Talking about this kind of infinite integral thing actually does have real life applications. They do not involve trying to paint infinitely long shapes like that. But anyway, can we discuss how could we actually calculate this area? I said last time it was less than 2. It's not equal to 2. 2 is the area of all these boxes together, and you can tell just by looking that the shaded area is less than that because it doesn't hit all those boxes. I mean, it's smaller than the boxes, right? How could we actually calculate this? To calculate the area, the area of that infinite shape, actually the area itself is not infinity, but to calculate this area, we approach this, the standard way that we approach infinity in all of calculus is to think of it as a limit. And so here's the idea. we do just a finite piece, by which I mean you just sort of choose some upper limit to the integral. You know, the true integral that we're interested in goes all the way out to infinity, but that, of course, is not something we can handle directly. So instead, we just do a finite piece. So when I say 1 up to t, that means, I'm drawing the same function here. That means you go from 1 here, and then you just go like maybe really far down, but not all the way, right? And that area there, that is definitely not infinity, because it doesn't stretch out forever, right? So this area, we can actually calculate that specifically. So we can find this area. It's not infinity, because that is now only a finite range there from 1 to t. So we can find this area and then express it in terms of t. We kind of imagine that t is a constant when we're finding the area, but then our answer for what that area is will depend on t, and then we can do the limit as t goes to infinity of that. So we find this area, express it in terms of t, and then do lim t goes to infinity. And what that represents is what would it look like if you had this area, but the t actually was sort of all the way out to the right. Is there too much glare on the screen?
Just gonna look at this one.
All right. Yeah, sorry, it's somebody opened the windows, which I like, but okay. This, I don't know if that sounds complicated, all of this description. It's actually very, very straightforward to write this down. I mean, it's a few extra steps in doing the integral, but it's not much of a problem. So let's just try this one. Oops. Let's just try this one. Integral 1 to infinity of 2 to the negative x. All right. What I said was, we, instead of trying to do the integral all the way to infinity, which doesn't really make a lot of sense, I change the infinity to a t, and then I do the lim t goes to infinity. I'm going to write, when you write that, really you can just write it all as one step. I am considering the lim as t goes to infinity, integral 1 to t, 2 to the negative x dx. All right. And then we just do the integral. So do the integral, and we, as we're doing the integral, we treat t like a constant. But since t is one of the boundary values, really the t being in there really doesn't affect very much of anything until the very end when we plug the values in, right? So we do the integral, treating t like a constant. All right, so I'm gonna, now what's inside the integral here? It's no funny business. I mean, sometimes you might have to do some weird tricks, the u substitution or the parts or something. But in this case, it's just an exponential function. I hope everybody remembers. It's one of these, right? It's an exponential function where the base is not e. Anybody remember the formula for this? Yeah?
Would be like a to the x divided by natural log of a.
Yeah, right. It's a to the x over ln a plus c in general. So that's what we're going to get here. Now it's a, we do have a minus x up top. The effect of that is it's going to make the whole answer negative. If you like, you could do a little sort of tiny u substitution, u equals negative x, and the effect of that would be to put a minus sign in front of everything. So what we end up with here is lim t goes to infinity, and then the integral 2 to the minus x becomes minus 2 to the minus x over ln 2. And then we're going to plug in the two values, and they are 1 and t. All right. You just do the antiderivative and then plug in the two values. Now, one of those values happens to be a t rather than a number, but really it doesn't matter. We just do the same old thing with those two values. So it's going to be t goes to infinity, negative 2 to the minus t over ln 2 minus negative 2 to the minus 1 over ln 2. like that. All right, now it occurs to me. Sorry, I just looked at my paper for the first time. I was just going off the dome here. I realized this doesn't really matter. Last time when we talked about this, I was talking about the integral from 0 to infinity, not 1 to infinity. It doesn't really matter. Now I'm talking about 1 to infinity. Sorry. If you want 0, just replace the 1s with 0s. It's not exactly the same, but it's the same idea. I thought I was continuing the same example from last time. This is very slightly different. Anyway, what do we do here? We have to do this limit, right? Now, this part here, nothing's going to happen when we do the limit because that's already just a specific number. You could figure this out on your calculator if you want to. It has a ln2. What about this part? What happens when I take the limit of t going to infinity? So really what I'm thinking about is the only part really that deserves to be thought about is that much, right? What is the limit as t goes to infinity of t 2 to the negative t? How should we think about that? The exponent is becoming negative infinite. I think it's the easiest way for me to think about this is to write this as 1 over 2 to the t, all right? That's what 2 to the negative t means, of course. And so now I see a fraction where the bottom is 2 to some super big exponent. Anybody want to say, what do you think this limit is? Yeah? It's going to be 0. Yeah, why do you say that?
Actually, when it's going to a super big number, it's going to be 0.
Yeah, right. When it's when you have a super big denominator in the fraction, that's going to be 0. Yeah, excellent. So this is 0. It's because I will just say denominator. I meant to write denom. I wrote demon. The denominator goes to infinity, which means this fraction as a whole becomes 0. So when we take the limit, that was a little sidebar here, but when we take the limit, this whole thing, what we're interested in, everything just stays like it is, except that thing right there becomes 0 when I do the limit. So this is pretty much the end. I do the limit, this becomes 0 over ln2, and then I have the rest of it minus, can I say plus? And then 2 to the minus 1 is really 1/2. This is the same as this. So my final answer is 1 over 2 natural log 2. That's what the real area is. Sorry, I'm off the bottom. That's what the actual area of that thing is. The area stretches all the way out to the right, but it is not infinity. This is something like this area. I put this in my calculator ahead of time. It's around like 0.7, right? I said it was less than 2. That's because I was starting from 0 when I was talking about 2. So, all right. Definitely not infinity. Excellent. Let's, I thought it might be fun to, oh, yes, I have one more interesting example. So, this is the definition. I will just say this, abstractly speaking. This is a definition of, like, what does it even mean to find the integral where the upper boundary is infinity? And this is how we always do it. So if I'm taking the integral up to infinity, and it doesn't really matter what the lower value, here I just wrote a. It could be any ordinary number down here, but infinity at the top. What does that even mean? It means this. Lim t goes to infinity, integral a to t, f of x dx. Right? That's the definition of what this means to put an infinity in the top. It means this. Really, you don't ever plug in infinity as one of the values. You plug in this sort of variable, and then after the fact, you take the limit as the variable goes to infinity. All right? That's the way that we make sense of this. And this is referred to as an improper integral. I don't really like this terminology, but because there's nothing really sort of morally improper about it. It's kind of like improper fractions. I'm totally fine with improper fractions. But they call it improper integral when it's going up to infinity. It does require some amount of making sense about what does it even mean when you put an infinity as one of the integration boundaries. All right, and I will say, because it involves a lim at some point, like you usually do a bunch of stuff and then you do the limit at the end, right? Because it involves this limit, since there's a lim in there, it's possible that the answer may not exist, right? Because sometimes when you do the limit of whatever, sometimes there just is no limit, right? So since there's a limit, it's possible that the answer will be undefined. I mean, if that limit that you're doing does not exist, then sometimes this integral, you say the integral does not exist, all right? Actually, there's special terminology that we use in that case. So when this limit does not exist, we say, you've probably heard this terminology before, we say the integral diverges. When you take the limit at the end there, if you end up saying the limit does not exist, then the terminology we use, we say the integral diverges. And when the limit does exist, so when the limit exists, we say the integral converges. Right? Converges means as you approach something rather than the limit, the answer actually does approach a particular value, versus diverges meaning the answer doesn't actually approach anything in particular. It just goes crazy somehow. That's the language we use. All right, let's just do one other simple example. How about integral from 1 to infinity 1 over x dx? All right. The graph of this one actually is similar looking to the graph of that exponential one. Everybody knows the graph of 1 over x. If I just look sort of on the right-hand side here, it looks like that, right? 1 over x. Very similar to the picture that we were drawing for that other example. I'm talking about this area here going up forever, from 1 to infinity. All right. So this is another example where, like, on paper, the region that I drew there seems to go on forever, but that doesn't necessarily mean the area is infinity, although maybe it is. I mean, you just have to work it out to see one way or the other. So let's work it out. The first step is to write this as a lim of something or other. So it's the lim t goes to infinity. I'm always going to call it t, although some books might call it something else. Our book always calls it t. 1 over x dx. And then we got to do the integral. All of your intermediate steps, you should be writing this lim every time until you actually do the lim at the end. Anybody say, what's the integral? 1 over x? Surely you all remember. Yeah. ln of x, yes. You can impress your grandmas over the break with that little fact. ln of absolute value x. All right, excellent. And now we plug the numbers. So this is lim t goes to infinity. I say ln t, absolute value t. The absolute values don't really matter because everything I'm talking about is already positive. And then ln of 1, all right? What can you do with ln of 1? Actually, that is something. What's the ln of 1? Someone to show me on the fingers? The fingers say this. The ln of 1 is 0, right? That's a basic fact about the natural log. And so this doesn't matter for anything. What about the other part? The natural log of t as t goes to infinity. You have to ask yourself, what if I plug really, really big numbers into the natural log function? Does it like become 0 after a while? Or does it also, is the answer just going to be really big? Anybody? This requires that you know something about, like, perhaps what the graph of ln of x looks like. Does it become 0? Does it level off? Or does it go up forever? Anybody remember? I see a lot of avoiding of eye contact. The graph of ln x looks like that if you graph this. So when I say lim as t goes to infinity, does this level off at some point, or does it become 0? It certainly doesn't become 0. It doesn't level off either. This just continues to go up forever. So the graph, this is the way that I would think of this. The graph of ln t looks like that. It kind of it doesn't go up very quickly. It goes up very slowly, but it does continue to go up forever. So that means ln of t in this limit, this actually, when t goes to infinity, this also goes to infinity. So this right here, this limit does not exist. Because as the t values go to infinity, the value ln t also goes to infinity. Oh, you see that low battery? I don't know if we're gonna make it. Your Mac will sleep soon. I'm living dangerously. Oh, I said 10%. We get another 20 minutes out of that? I don't know. All right. Everybody's hoping. So, what's my conclusion? So, this integral, 1 to infinity, 1 over x dx, diverges. All right. The interpretation of that, sort of informally speaking, it means that this area, 1 over x, this area here stretches out to the right forever, and that area really is infinity. All right. And it's not easy to tell just by looking at the picture. You can't tell really. But this area really is infinity, all right? It goes on forever, and also its area does not exist. I mean, the area is not a particular number. It's infinitely big, all right? I thought it might be fun to look at. You can kind of see the difference. On my pictures, of course, this picture here looks pretty much the same as this picture here, whereas even though this picture actually the area does exist, it's not infinite. Here the area is infinite. But I thought it might be fun. I got my little, I got my Desmos going here. This is a graph. Get rid of this. This is a graph of 1 over x. And so this area, just starting from 1, going out to the right forever, that area actually is infinite. This is 1 over x, the bigger one. That one really is infinite. And you can tell that like the curve does get closer and closer to the x-axis, but that line or that region is still kind of thick, as it were, even as you're going out to infinity, all right? And it turns out that that region is sort of thick enough so that the total area going out to infinity really is infinite. Whereas here's 2 to the minus x. The blue one is 2 to the minus x. That one, the area is actually finite. That's the one the area is like less than 2, right? And you can see this one, as I go out to the right, very quickly becomes like completely invisible, all right? So both of these regions technically do stretch out forever to the right, but you can see with your eyes that one is a lot bigger than the other one, even though like when I just draw the graphs, you can't tell, of course. All right. The red one is 1 over x. The blue one is 2 to the minus x. The blue one is actually quite a lot smaller when you go out to the right. All right. I would like to discuss, you can see over there, 1 over x squared and 1 over 1.1. So I had you all to try 1 over x squared. So remember, 1 over x, this integral up to infinity diverges. But 2 to the negative x, 1 to infinity, converges. What about 1 over x squared, right? This one, the graph of 1 over x squared, again, it looks, I mean, informally, it looks the same as this. It's just like the curvature of it is slightly different. But I would like for you all to see if you can work it out. Work out the integral and see when you take that limit, do you actually get an answer or does it become infinity again? See what you think. First thing you do should be to turn it into a limb of something. Nothing to do with the LM this time around. Can we discuss? It looks like people are doing fine here. Everybody eventually realized that this is x to the minus 2, and so to do the integral, you go minus x to the minus 1, and then I need to evaluate this at t and 1 as my two endpoints. Putting in the t first, so I have lim. Plugging in the t first gives me minus t to the negative 1. Subtract minus 1 to the negative 1. All right. Now these negative 1 powers, I prefer to write them as fractions. This says minus 1 over t, and then plus 1 over 1, which is 1. And then what happens when t goes to infinity here? This is a fraction having infinity as its denominator, and so that fraction part becomes 0, and all that remains is just the 1. So this is just 1. All right. Because this part becomes 0. When you take the limit, the denominator there is going to infinity. So the area under the curve is 1. All right? So that means 1 over x diverges, but 1 over x squared converges. So 1 over x squared, this area, 1 to infinity, converges. That area is not infinite. Even though 1 over x, it is infinite. This is to me, this is very strange. But the area 1 over x up to infinity diverges. Even though these are very similar functions, looking at their graphs, they actually look the same. One looks like that, and the other also looks like that. It's just one is kind of like, somehow the curve on this one is a little tighter. But they really are quite different when you consider the area under the curve. For 1 over x, that area is actually infinite, but for 1 over x squared, the area is actually just 1, which is quite different from infinity, isn't it? Here I decided to put that in my little Desmos too. So this red region is for 1 over x. If I do 1 over x squared, it's that green line, and you can see the area under the green line really is quite a bit less than the area under the red line. So we just determined the total area under the green line going out forever is actually 1, whereas the total area under the red line is infinite. Very strange but true. All right. What about 1 over 1.1? When I see this, the fact that these two things are different, like I said, is kind of surprising to me because on the surface they look fairly similar. They are different and like kind of very different. Like this area is 1, but this is infinity. Like they couldn't possibly be any more different. And I begin to wonder, what if you change the 2 a little bit, make it like 1.9, then 1.8, like eventually, if you make it into a 1 here, then it's infinity. But what if it's like somehow close to 1 but not quite 1? What is that? That's why I decided to draw this next one that I'm going to turn on. It's 1 over 1.1. It looks like that. That's the blue one there, which you can see is quite close to the original red line. It turns out that one is also finite. If you work out the details, I don't think we need to work out all the details by hand here, but can I just say, will you believe me if I say, similarly, if I do this as a 1 over x to the k from 1 to infinity dx, so we just did it for like k equals 2, but if you, instead of 2, if you use something like 1.5, you would do exactly the same steps, and it comes out more or less the same. It turns out the limit would exist. The reason why 1 over x is special and different is because you get ln of x here, versus over here you just get like some other power of x. And so this one also converges, I will say, for k being positive, more than 1, right? When that number here is greater than 1, it converges. When it equals 1, or when it's less than 1, it diverges. So this is kind of an important fact that I wouldn't say you have to remember this, but well, you should remember it. I'm not gonna sort of make you memorize this, but I'm gonna write this as a theorem. This is fairly important. It says the integral from 1 to infinity, 1 over x to the k dx, converges when k is greater than 1, and it diverges when k is less than or equal to 1. All right. This is important, and this is actually going to come up again towards the end of the course when we talk about the sequences and series, which is our sort of major block of topics at the end, which is not that far away actually, but this will come up again when we talk about sequence and series. All right. I think we got a few minutes. Let me just do one more quick example. I guess my computer is going to survive. 2%. We'll see if they can handle one more quick example. This is not terribly fascinating, but I want to get it down. We can also do improper on the bottom. So all of the examples we've been discussing have been infinity at the top, but you can put infinity at the bottom, although infinity at the bottom usually doesn't make a lot of sense, but minus infinity at the bottom certainly does make sense. So here is just a simple example. Minus infinity to minus 2 of 1 over x squared. All right, so this, if you were to draw this region on the graph, it's just like a region stretching out to infinity going to the left rather than to the right. But anyway, we do it in exactly the same way. So can we just real quick work this out? The only difference is the limit now is t goes to minus infinity, but then you put t up to 2. And x to 1 over x squared, of course, I'm going to write as x to the negative 2. The limit is t going to minus infinity this time. And that only is going to matter at the very end when you actually do the limit. So we do the integral. Lim t goes to minus infinity. The integral is minus x to the negative 1. I plug in minus 2 and t. So we get minus negative 2 to the minus 1 minus t to the minus 1. All right. Negative 2 to the minus 1 is 1 over negative 2, of course, and then there's another negative. So this is actually just, I'm just simplifying a little before doing the limit. This is just a half and then plus 1 over t. And then what happens to 1 over t when t becomes negative infinity? Again, this is a fraction where the denominator is infinite, although it's negative infinite, but it doesn't matter. You're going to get 0, right? It's 1 divided by some huge negative number. It shall